All right, everyone. So welcome again to this special guest lecture that we have here. So far in our class, we've been doing all of the optimizations to get to a smaller, more compressed, quantized, prune model. But we're using that just in the kind of model framework, just in the sort of the software API. And we are still compressing it and taking it down to like a microcontroller, which is essentially like a single threaded processor. That is a conventional processor. It's for like kind of legacy software. And so today I want to show you, well, what can you do that could be like an order of magnitude or order of magnitude more efficient than just only in the software realm, but going to the hardware. And that's where Professor Rob Radway, he's going to talk to us about how do we start from ground up? How do we rethink, the design of the processors, but with machine learning as a first-class citizen? And then how do we take the models that we design in software and convert them through compiler frameworks, through optimizations for specific kind of hardware, right? These are neuromorphic computing frameworks and neuromorphic computing hardware. So let's learn about what this all means and how you can then go end to end from a better design, but with machine learning as a first-class citizen. So please welcome Professor Robert Radway, and he's one of the newest professors in our department, doing very exciting stuff. And he got his PhD from Stanford and has had several firsts in designing, this entire pipeline. Welcome.
All right, so just some level setting. So everyone's heard of like machine learning accelerators, right? Building custom hardware to accelerate machine learning. So when I say ASIC, does anybody know what that means? Yeah. Go ahead. Yeah, so application specific integrated circuits. So today what I'll be talking about is mostly how we build better ASICs for machine learning at the edge. And not just thinking about the algorithm design, but also thinking about the hardware design, the choice of memory technology, how we build scalable systems, and how we think about new integration techniques to scale up to larger and larger machine learning models. Now, I know a big focus of the course here has been on ML, but in general, a lot of what I'm going to talk about today applies beyond just machine learning. So thinking about how we take the massive amounts of data that we generate in today's society and use them to power changes in healthcare, in scientific computing, things like augmented and virtual reality, and then also specific machine learning applications. So a big focus of this course has been on solving some of this problem, right? Which is traditionally, when we think of machine learning, specifically for training, but also for inference, what does ChatGPT do today? Does anybody know the pipeline, how it works? When you type something in, where does the model get run? Yeah.
It's run in some data center and then it gets sent back.
Right. So all of these AI companies are building massive data centers. They're talking about building their own nuclear power reactors to power these data centers. And the big problem with all of that is basically when you have some device that's generating some input, be it you writing in the text or your camera that wants to do some image recognition, you have to send that data from your device to the cloud. And that's actually quite expensive. So on the order of, nanojoules to microjoules per bit of data transferred. Once that data is in the cloud, then everything is run there, and then you have to send your results back. And this actually has a host of concerns, and we really want to move to running our machine learning models on the edge. So actually computing where the data is generated on the same device. This saves that energy, so we have massive energy efficiency gains. It actually helps deal with a lot of the issues of scalability from a power perspective. So if everybody is using their cell phone or their tablet or whatever to run the machine learning model locally, then you don't necessarily need that massive nuclear power plant to run a massive data center to process everybody's results at the same time. It's more responsive, so you get a response faster, and it's private. And so for specific applications, think healthcare, military applications, but also then things where you might not want people to have all of the images that you see every day or your speech constantly recorded and sent to the cloud. You could process on device and have privacy guarantees. The problem with this is that machine learning models are big. And if we look at the actual source of energy consumption, a large portion is in accessing memory. So anywhere from about 2/3, even some larger LLMs, it's more like 90% of the energy consumed in running the model is reading from memory for the weights, writing back your intermediate values, and then reading those values to keep doing your computation. So this is a real problem. And unfortunately, the traditional approaches that we have to solve this problem are no longer scaling. So everyone's heard of Moore's Law? Yes, okay. So Moore's Law is actually a cost argument. It's that every year or so, we get twice the devices for the same cost, or each device gets half as expensive. And the reason that that was kept consistent is that basically, as we go node over node, as we go to more advanced geometries, we have finer and finer lithographic features. And so we could scale down our memory cells to be smaller and smaller. Unfortunately, within the last 3 to 5 years, that scaling trend has completely stopped. So we already lost out on Dennard's law, which was the energy efficiency scaling trend that went with this. But in terms of our ability to pack more machine learning weights in the same area, we're basically at a wall, hit this wall. So that's where a lot of the topics in this class around quantization, pruning, sparsification, building efficient pipelines with a limited amount of memory capacity have become very important. However, I'd argue that even those solutions are not future-proof. They're kind of a one-time gain, right? So if we start with today's machine learning model that is a gigabyte in capacity at 32 bits per weight, and we could prune it down even to 2-bit weights. Tomorrow's model, if it's 8 gigabytes of weights at 32-bit, is still much larger, even if we keep pruning to 2 or 1-bit weights. So there's nothing we really can do if we require more complex, higher weight count models to do more complex tasks. And that's where a lot of the work that I've been looking at comes into play, which is how do we actually get through this miniaturization wall? How do we redesign our system to avoid spending so much energy in accessing memory and overcome these walls to build new computing systems? So I'll talk today about 3 main ideas and hopefully make the argument that
Just trying to see.
Yeah.
I can mute the audio. Probably
Best. Oh, you know what? Test. Oh, if you disconnect from this, then it'll not have my test. Okay, good. All right. So, I will argue that there are across the stack optimizations required, starting from thinking about how we build new machine learning accelerators using different types of memory, how we scale those to different systems, and then how we look at advanced integration techniques where we combine new transistors, new memory cells in order to improve the capabilities of both the chip and the system itself. And In general, if you're interested in these types of research activities, there are lots of interesting optimizations you can do. So I've done work everywhere from individual chip design to working with foundries to building, advanced ASICs to building full multi-chiplet systems. So it takes a lot of different aspects, right? Software, there's the whole chip design process, there's understanding the transistor integration approach and how we actually fabricate these devices. So if you have interest in any of those areas, machine learning chips and systems are a great, motivating example because we have to do these improvements all the way across the stack. So when we think about designing a custom ASIC, the first thing is, what are the application needs and what's the right technology to meet those needs? From that, you've developed, okay, I have a specific transistor and memory technology. How do I build circuits, architecture? How do I integrate those different components in order to meet those needs? And then can I take algorithmic innovations, so things like quantization, things like sparsification, pruning, et cetera, and apply those to improve the capabilities of my system? And a lot of my research has been focused on the hypothesis that edge-to-edge machine learning systems, in order to build a full capable system, you need heterogeneous combinations of different memory technologies. So not just the SRAMs, DRAMs, or flash memories that are very common in today's computing systems, but other memory devices. So next semester, I teach a course that specifically covers this, 5760. So if you're interested, I would suggest taking that, but this will give a little bit of an overview of the motivation of that course. So let's think about edge machine learning. How is it different in terms of inference compared to the cloud? Does anybody have any ideas? What's a key difference? So yeah, go ahead.
Yes, one of them is that you're way more resource constrained.
Yeah.
On a device with no cloud, which is theoretically unlimited. And then, well, not really unlimited, but a lot more than.
Yeah, so let me rephrase the question. What is a key difference in terms of how the inferences occur? Not necessarily the resources, but how do inputs come in at the edge versus how do they come in at the cloud?
The sensors are processing as that.
Yeah. And how often does that happen?
We just whenever.
Exactly. So at the edge, we are basically user response driven. A user takes a photo, they want to know, what is the language that's written in this photo? Is it, Japanese and translated, or is it Chinese and translated, et cetera? So that's like an inference request. In the cloud, you have an aggregate set of users all making these requests at different times. And so on the average, you kind of receive a constant stream of requests. There's always some new data to be processed, right? Because if you have 1 million users, the probability that someone is requesting something at any given point in time is very high. But for the individual user, that's not the case. So when we look at how machine learning systems are traditionally benchmarked, they look at two main characteristics. Throughput, so how many samples can you process in a given amount of time? So inferences per second is a common way of referring to this metric, or tokens per second if you're thinking about LLMs. And that is a good metric when you have this constant stream, because it also, if you maximize your throughput, you tend to minimize your energy, right? Because you're ideally using the full power that you have on your chip constantly at the highest throughput possible, and that would minimize your energy per inference. So if we look at those as two metrics, right, we have the average time for each execution that determines our throughput, and we have the average energy for each execution. So this works great in the cloud, but at the edge, this isn't the complete picture, right? So we actually have this variable time in between each inference where we're idling. And that means that the total energy is no longer just these large boxes where it's the energy of the inference, but we also have to account for the energy of idling, right? So if you have your phone and you want to maximize its battery life, if it's sitting there spending a ton of power just existing to keep your machine learning model around when you're not using it, you're going to drain your battery life. Instead, what you need to really think about is, how do I manage the entire energy picture? And that's where joint metrics like system level energy delay product which is considering both the multiple of the time of execution and the energy of execution, plus accounting for any idle in between the average length of our input arrival time. So who can think of an easy optimization here? How can I improve this metric without actually redesigning my ASIC? Without changing even T0 or E0? What's the easiest way to improve this metric? Yeah. Exactly. Turn off the chip. That's the easiest way to do it, right? If you could turn everything off and shut down, and then you only turn on when an input arrives, then you minimize all those idle powers. It seems very simple. It's actually very hard to do. And the reason it's hard to do is because of constraints on our memory technology. So when we think of memory, you think that, oh, it's always going to keep the data around, right? If you write something to your hard drive, that data should be there the next time you boot up your computer. Same thing with pictures on your phone, etc. The thing is that actually different memory technologies have different retention times. Some require constant power. So SRAM requires constant power in order to keep its data. Flash or disk doesn't, but those have much higher access energies and latencies compared to SRAM. So there's this trade-off space. And ideally, what we want to figure out is how do I build a system where maybe I have just a small amount of the chip on. When I get an input, I quickly turn on the whole chip. Then when I'm done processing, turn everything off and just repeat this process. I want to do this quickly, so I need to make sure that this on-off is very fast, that it doesn't consume much energy, and that through this shutdown, I'm able to retain the machine learning weights. Because if I have to go and fetch a set of weights from the cloud or fetch a set of weights from disk, something very slow, every time I do this boot up and shutdown procedure, then this is going to take a long time, and I won't have the energy gains that I think I will. So what we did in starting to work on this, and this was almost 7 years ago now that I started on this project, but we looked at all of the memory technologies that were available at the time. So commercial technologies like DRAMs, embedded DRAMs, SRAMs, flash memory, embedded flash memory. So most of the microcontrollers that you guys are working with will have eFlash and SRAM. And part of the issue is that none of these memories is actually sufficient for this ideal situation. So you want something that's non-volatile. You also want it to be on chip because that means that you have very fast reads to the memory, very fast writes, and they're very low energy. You want that low energy. You want it to be dense because you want to store a large model. You want it to have high endurance, which means you can write to it many, many times, because if you're doing any on-device training and customization of your model, you need to be able to update those weights. And you want something that is scalable to future nodes. So embedded flash, for example, we can't really build below the 28 nanometer, 22 nanometer node. After that, it becomes prohibitively cost expensive to build. So that's why SRAM has been the dominant memory, but SRAM is also not scaling anymore. So what we looked at was saying, okay, what if we take a heterogeneous combination of SRAM, traditional memory technology, we use that sparingly, with new non-volatile memories. In particular, a memory that's called resistive RAM, which I'll explain what that is briefly. If you look at the average of those two boxes, everything's green, right? If I can combine these two memory technologies correctly and use them in my system, then I get something that is on chip, non-volatile. I have low energy reads writes, it's dense, it's scalable, and it has high endurance. The trick is, how do you figure out how much SRAM you need, how much RRAM you need, what the right combination is, which memory you use for what part of your machine learning inference, and how you design the custom ASIC to take advantage of these properties. So a brief aside, if you're really interested in learning more about devices or these different memory technologies, we go many lectures on this in my course, but basically RRAM is a way of having a programmable resistance. So think of it as like a potentiometer, if you guys have used those in a circuits class. It's a two-terminal device. You have some process by which you can change the resistance. That resistance encodes your data, right? So if you have a high resistance state, we'll call that a 0. If you have a low resistance state, we'll call that a 1. We can read that out, but this conductive filament that forms the resistor, it's non-volatile. So if you take away power from the terminals, it stays the same. Just like in a potentiometer, if you don't twist the knob, the resistance will be the same when you get back to that circuit. So this is great because it gives us that ability to store things non-volatilely. But what's also nice is that it's actually very readily integrable. It's easy to manufacture. And so it has all of those on-chip, low energy and scalable goals, features that we desire. So we looked at comparing these systems and this quick on-off behavior. And basically the key takeaway was that as we looked at a full end-to-end microcontroller using a non-volatile memory like RAM versus a traditional memory technology like embedded flash lets us have quicker shutdown, lower energy shutdown, and reduce our overall power because it's lower energy to read that memory, right? That 60 to 70 to 90% of memory access energy is reduced to almost 10%. And that gives us a large energy savings overall. So we took this idea, this was some initial work at the start of my PhD, and now we said, okay, well, we built a microcontroller, that's interesting. We could do very small models. This was like 8 kilobyte weights. So stuff like, tiny ML models that were many years ago. Then we looked at building convolutional neural network systems for both inference and training using foundry supplied RM. So this was a kind of pre-foundry process. And then we built a full system for transformer inference, right? So doing language translation, sentiment scores, all those types of things, both inference and fine tuning on device using this idea of combining RM and SRAM. And again, the key insight is that basically this idea of really quick turning things on and off, it's not only at the inference level, that you could actually apply that at the circuit level and turn off the components of your system that are not actively used at a given point in time. So what's one feature of, we said, okay, inferences come sporadically. And during that inference, I want to be computing. And in between the inferences, I want to be off. But what are deep neural networks? What feature do they have that would also lend itself to this idea? Does anybody have a guess? I'll give you a hint. It's in the name. Deep neural networks. What feature do they have? So they have, yeah, go ahead.
They're only one layer.
Exactly. It's a sequential process, right? You have this depth of network, and it may be many layers deep, but for each layer, you only read a subset of your memory. That subset of your memory is the only thing you're using for that point in time, and then you go to the next layer, and then the next layer, and the next layer. So only for any slice of time while you're actively computing, you only need a small portion of the total memory, and there's a huge energy savings to be had by taking this idea of power gating and doing that at that very fine granularity. So if we could actually turn on and off our components of our system such that we're only having the memory that's actively being read on when it's required, then that minimizes our total energy. It's actually very hard to do. So this requires both circuit implementation details, right? How we actually do this power gating, plus compiler tricks, right? We need to be able to think about turning on and off components of our system in our compiler. And most compilers by default do not consider power at all. They don't consider the idea of being able to turn off components of your system because you generally think of, you're computing, von Neumann style architecture. You have your compute unit, you have this sea of memory. Anytime you request a word, that's brought in from memory. So the idea of having something off breaks that fundamental assumption that you could request a word of memory at any time. So if we can combine these two ideas, then we get major energy delay product benefits, not only between this idea of inference to inference, but also within each inference itself. And so that was, a key innovation. And also, it turns out that RM is really great for all of this because we can do very, very fine-grained power gating, turning off individual banks of the memory, individual chunks of it. And we still use that same feature that it's very quick to turn on and off, and it's non-volatile to our advantage. So I'll pause here. Any questions? Because this is a little bit high level. Yes.
I feel that some of the memory scaled down to smaller application sizes.
Yeah.
So what is the base?
Yeah. So if you look at the cell, this is a good example of this. Basically, the top and bottom of electrode are metal features, and this is an oxide. This is an oxide. So you can actually fabricate that at the minimum metallic density or metallic feature size that you can fabricate in your technology. So there is this idea of feature size, it's called F in scaling. So this is a 4F squared memory in its best implementation, where you have the metal pitch for the size of the square times 2 for the space. That's the maximum density that you can fabricate it. It's a very dense memory technology. SRAM requires 6 transistors. Each of those transistors is many F. So SRAM is something like 130 to 160 F squared. So many, many times worse in terms of its density. Other questions? Okay. So to prove this idea out, I think just like you, because this class has labs, correct? You have to demonstrate some of the quantization techniques. So we not only have to figure out how to implement machine learning on hardware, we have to build the custom hardware to show these ideas. And the reason for that is that whenever you're doing some of this fine-grained power management techniques, your simulation techniques for the circuit are not very accurate. And the best proof that it works is that you have hardware that you've measured showing that it works. So we built a whole inferencing system. This is for the transformer case, but the convolutional case is very similar. You basically have a custom neural network accelerator. I'm not going to go into a ton of detail on how these are built. If you have interest in that, I would suggest Professor Jing Li's course, hardware software co-design for machine learning. I don't remember the course number, but that covers a lot about how these accelerators are designed. But think of this as a sea of very small multipliers. And those multipliers do your tensor operation very energy efficiently. We have a tiny RISC-V CPU. So think of this like a microcontroller that controls everything in the system. Some memory to control our instructions, store our instructions. And then again, the SRAM and the RRAM, the two heterogeneous memory technologies. RRAM is basically for the weights. SRAM is for the activations. So we can use those different banks. And we built this whole thing without any off-chip memory. So whatever capacities we had, whatever compute capabilities we had to assume that was the only thing we could do to fit our machine learning model. And this is that space-constrained, resource-constrained approach that a lot of this class focuses on, right? How do you actually take models and compress them, let them work on a specific neural network accelerator or microcontroller architecture, and do so such that both the results are correct and energy efficient. So that is a whole process, which I'm sure you're familiar with by the end of this course. But some of the key takeaways, one is a really big chip. I should have brought the actual chip. I could have passed it around. Sorry, I forgot. But it's pretty interesting to see. This thing had almost 400 pins, so 400 inputs. We had to do a custom package, all the whole shebang to make it work. This is what it actually looks like in terms of the layout. So remember how I said memory is a large part of the energy? Well, in today's machine learning hardware, memory is pretty much all of the area too. This is the actual accelerator, a small slice, and a large part of that is actually SRAM that I'm not even showing. There's buffers and other small memories in here in the accelerator. Then we have SRAM for our activations and then RRAM for our weights. So basically 8% of the chip is actual compute. The rest is basically memory. So that's why there's such a focus now on new memory technologies, denser memories, scalable memories, because they dominate the system design. And if you look at today's GPUs, it's very similar. Most of the SMs are actually SRAMs, and then the whole package is mostly DRAM. Yeah.
Would you only use the SRAM if you're doing the on-device?
No, we use it for buffering, right? So when you get your first input, you need to store that entire token string somewhere. So that goes into the SRAM. Then you do your tensor operation for the first layer, and you have intermediate values every layer. So you write those back into SRAM. So the SRAM is effectively, it's called a double buffer. So for both the inputs and the outputs of each layer, and for training. So we don't need 2 megabytes for like the BERT and other transformer models that we were looking at for just the inputs and outputs. You only need, I think it's like 100 kilobytes, something like that. But you do need 2 megabytes in order to do the training techniques, which I'll briefly touch on. So what ends up happening is if you can design the system correctly, if you figure out both your memory architecture, how you connect your memory to your accelerator design, and some of the aspects of like that buffering scheme, etc., you can get really high utilization. So that means that this thing is computing basically every clock cycle. It's almost fully utilized during the computation. We can reduce our static power by doing that fine range on-off and shutdown. We can actively manage our memory power to be 3.3 times lower using that very fine-grained power gating idea that I mentioned. And you can enable new training if you come up with new algorithms. So again, the idea of new devices all the way up to new machine learning algorithms is pretty important. You have to think about combining innovations in all those areas in order to, say, enable your own customization of a transformer on a given user's chip in an energy efficient way. So questions here? No, okay. So let's go a little bit into some of those details about the power gating. I'm just going to briefly go through this, but there's actually many variants of what we would consider turning something off. So you can actually turn off the clock of the chip, and so it's not computing or not reading out data, but it's still sitting there statically idling. You can shut down parts of the macro. You can shut down the whole macro controller. You can shut down the entire chip. Those have different power levels. And so what we had to do was actually figure out, okay, which of these circuit implementations actually gives us the savings that we expect versus an SRAM, which is constantly sinking power to keep the data around and turning the RM off. And it turns out that you basically need to fully shut down both the macro or the entire chip in order to have that maximal savings. And so the idea of doing that fine-grained turn off means that we're going between, effectively this mode and this mode very quickly. And it required quite a bit of physical optimization, how we implemented that to make it quick. So we could actually turn these on and off in 5 microseconds, which is very fast when you're talking about 10 millisecond inference times, 10 to 100 millisecond, depending upon the model. So that ends up giving us quite a large benefit. And so if we take the system and we look back at that, yeah, go ahead.
So to get these power savings estimates here, do you have to build out the system or can you do this in?
This is from measurement, but we had simulation results that projected this as well. So in chip design, you have power estimation through activity propagation, which I'm not sure how much this class will know, but basically you can estimate how often each of your logic gates is switching, and that tells you how much you're charging and discharging the parasitic capacitance in that cell. For memories, they have from the foundry, they have models that say both that, the dynamic power, but also how much power is just consumed statically sitting around. So we can actually simulate for each of these optimizations what the power change is, and therefore the energy savings that we would have.
And the simulators are pretty accurate.
The trend is there.
Yeah.
The values were off by quite a bit. Yeah, especially for some of these newer, like for the SRAM, it's perfect. Like your SRAM model is almost always going to agree with your chip if you know the right corner for the chip. The RM model was relatively new because at the time we got this, the memory was still not commercially released. But the trend was the correct trend. So this was to go back to that idea of power gating as a way of saving inter-inference, and then I'll talk about within each inference how much energy we saved. So we can look at taking RM, SRAM, or off-chip flash. DRAM and SRAM, those require static power or refresh power. They're constantly leaking energy in order to keep the data around. And so as you go from 100% duty cycle means you're inferring like in the data center constantly to very infrequent inferences. So one cycle out of every 100 is actually for inference, or out of 1,000 or 10,000. Our RM energy is basically the same because our wake up and shutdown is very low compared to the energy of inference, and so we keep the same energy per inference regardless of the duty cycle. With SRAM, or DRAM, as you spend more and more time between inferences, you're leaking more and more power. And so your average energy per inference goes up and up and up. And you can use off-chip non-volatile memories like flash or eFlash, but that basically just sets a ceiling because it's very expensive to read that data. And so only after leaking for a long time does it become cheaper to shut down the SRAM and refetch the memory from the flash storage. So the end result is that basically these RM systems have anywhere from like a 9 to 18x, depends on the system size and a bunch of other factors, energy delay product savings. And most of this is really just in energy. There's not really any difference in performance in terms of the inferences per second that you can achieve with the two systems. So that was the first idea, right? At an inference level, we could do this fine-grained power gating, but within the inference, we can do the same thing. So if we actually look at, and this is for ResNets and MobileBert, which is a small transformer model, if you look at the amount of memory that's required, as well as the bandwidth required by each layer for a given accelerator, it can vary drastically. So this is actually about a 4x range in bandwidth, the gigabits per second required for your memory to keep your accelerator at high utilization. So what that means is that we could actually think about different bandwidth modes where we're turning on and off the memory banks so that we only have the right number of RM banks active to supply this bandwidth. And so what we ended up designing is a system that has the ability to switch between 4 different bandwidth modes, from 0x bandwidth, which is basically all the memory off, all the RMs off, 1x, 2x, and 4x, which is 1 times, 2 times, and 4 times as many banks on at a given time to supply these various bandwidths. And
what is in this? What is being exchanged for this high bandwidth?
how do you do it? Are you saying?
What is being exchanged in the model? But why does the model demand this?
Yeah. So the big difference is whether it's like a dense layer or a sparse layer. So in convolution, your feature dimensions are determining how much weights you need to read. And then the step size that determines how often you need to read them, because you can read more inputs for the same set of weights. So it's the weight reuse that you have within each layer. That's for convolution. For MobileBert, some of the layers are weightless, right? Like your KV multiplication, you've already computed K and V, so you don't need to read any weights for KV, the multiplication there. So you can turn everything off from the weight memory. And then each of those tensor operations, some are large matrices, some are small matrices. So you end up having a different bandwidth requirement for a fixed compute unit. If you change your accelerator design, this all changes. So this is for a specific accelerator design in a specific technology that is optimized for RM to begin with. But even if you've done that optimization for an RM memory, you still have this, 4x range of, I mean, it's technically infinite x, right? Because 4 divided by 0, but 4x range of bandwidths that you might need to supply. And so we can turn on the banks as needed. And what this ensures is that basically we have energy proportional access. So the idea is that if we want our memory to have the same picojoules per bit read, the same energy per read, regardless of how much bandwidth we're accessing, then we want to make sure that the number of RM banks that are on is proportional to that bandwidth need. So for example, in our system, we had 12 1 megabyte banks. Well, you can only ever read at max 4 of the time. It's a design limitation of our accelerator, how much area we had for our accelerator. So if you had 12 banks on, but you're reading 4 at a time, you're just wasting, you're wasting a bunch of static power versus the actual amount of dynamic power you're spending reading the memory. And so if you can turn down from 12 on to only 4 on, then your static and dynamic are much closer to the right proportion that you would have with 2 for 2x and 1 for 1x. And so what this non-volatile memory lets us do is what's called energy proportional computing, which is a very difficult goal, but lofty goal, where if you only ever spend the energy you need minimally to do a computation, then that is the energy minimal system for any machine learning inference. So we were able to do this, and it ends up looking something like this, where, oops, I click through, where, okay, during an inference, if I'm in a 1x mode, I'm reading through different banks at a time. And I'm, getting data sequentially across the banks. In a 2x mode, I'm reading pairs at a time, and I still have the same pattern pairwise. And then in the 4x mode, I'm basically reading clusters of 4 every time to read through. Now, this requires a ton of optimization, not only from the circuit side, but from the compiler, because you not only have to figure out which weights are required for which bandwidth mode, but how do I place the weights in the given physical addresses such that I enable all of these bandwidth modes correctly. So for example, if I have a layer that requires a 4x bandwidth mode, but I physically place it in block 1, 5, and 9, I can't read those in parallel at that 4x bandwidth. I need to have the memory sharded across blocks 1 through 4, such that I'm reading all 4 banks in parallel to get that higher bandwidth out. So this requires, I have a graphic of this, but yeah, it also has a predictive feature where if you already filled something with 1x bandwidth mode, that means that those other banks can't actually be read in a 4x bandwidth mode. Because if you were to try and put a layer sharded across those 4 banks, there's no space in one of them. So you'd have a memory conflict. So the compiler has to be aware of this. You have to do some sort of greedy fill process where you first assign your 4x mode. Then I think there's no 2x mode in this example, but then the 1x modes, or 2x modes and then the 1x modes, such that you basically shard your tensors correctly across the memory. So this gets into the nitty-gritty of how you design your linker script, right? And how you do all of that planning aware of these power modes. And the default C compilers don't do that. So we had to figure out how to do that, write our own custom compiler for this, own custom linker and memory allocator script at compile time in order to enable a large range of these models. But the end result was that this gave us a lot of energy savings. So basically, from going always 12 banks on to our bandwidth optimized mode, had a reduction from 2.9 to 3.3x in terms of energy. And the naive solution would be always have this minimal 1x bandwidth mode, but that means you're bandwidth starved for some of the layers that need higher memory bandwidth. So that would actually have a 1.7 to 2.4x slowdown from this bandwidth optimized. So really it is the EDP optimal solution. We're not sacrificing performance for energy. We're at the peak performance and the highest energy efficiency. Questions here? I know this is a lot. Yes. Yeah, so if you have something that requires lots of writing, like training, RM is not the best. So RM is very expensive to write to, but it's cheap to read. So for inferencing, it's very good, but for anything that's online training, you have to come up with new algorithmic approaches, which I'll briefly mention. In general, though, if you have models that have this like high dynamic range of bandwidth requirements, RM is very, very good if you do this implementation. So transformers, CNNs, actually most ML models have this, except for dense networks that are like uniform dense. And other questions? Yeah. This one or the right one? Oh yeah. So the right one is just saying that if I have everything on, that's 12 banks of bandwidth, so it ends up being max 4, or I could do bandwidth optimized, or the naive approach to be energy minimal is to only have 1 bank on at a time. But 1 bank provides 1/4 of the max bandwidth. So if I were to do that 1 bank mode, my runtime is much higher because I'm bandwidth starved. So it's better. That's what we're showing is that the bandwidth optimal is both performance optimal, lowest execution time, highest throughput, and energy optimal. So you achieve both versus a naive solution, which is to just do this 1x bandwidth. Other questions? Okay. Oh, what time is class at? That one is 10. Oh, okay, it's off from daylight savings. Yeah.
Yeah.
So we have another 30 minutes.
Yeah.
Yeah. Okay. So
20 minutes.
20 minutes. Yeah. So this is just to let you know that, you can't do all of this without accelerator innovations. It's like how you actually do that neural network accelerator has a lot of architectural, micro-architectural details. I'm not going to go over those because I think it's too much, but those are required in order to have these performance benefits. And in order to do things like training, we have to overcome this issue of RM, which is both its write energy and its endurance. So you can only write an RM cell about 10,000 times and it fails after that. If you're thinking about doing training on the device, a user might not have 10,000 inputs to train on, but over a lifetime, they may. If you try and train on every input and update the weights every time, you will run into endurance failures and that will cause performance degradations in your training. So you need to look at new algorithms. The specific ones that we looked at are basically variants of low rank approximation techniques. So there's one that's a LRT, and then there's another technique that's called low rank adapters, which is actually quite popular now in the academic literature. Those let us tune how often we write to the RAM while using very small amounts of SRAM to do the training. So we basically hold a compressed version of the updates to the weights in our training iteration in SRAM. I forget who was asking about the 2 megabytes, but that's what you need that 2 megabytes of SRAM for. And only infrequently project that onto the RAM to write back. So someone asked about scalability. I think it's really interesting. So this was last year, but basically after all of our work, we are actually seeing industry kind of buy-in. So Infineon has a whole line of RAM products now for their automotive microcontrollers, and TSMC is actually invested. They've already now shown an updated version of this with Pen 2 of scaling these memories into very advanced nodes, and still, they expect to see density gains as we keep scaling, unlike with SRAM. So again, if there's a key takeaway, application needs give you the right technologies. From those technologies, you can combine new circuits, algorithms, and architectures to get large energy savings and performance benefits.
So any of the mainstream, like say Apple or anyone, are they going in this direction of specialized memory on chip RAM?
Yeah, so I think the RM was only this was in 2014, the beginning of 2014, and this was basically the splashy announcement that TSMC has commercialized it. Sorry, 2024, not 2014. So a year and a half ago. So a lot of these are still maybe a little premature for the big players to put a lot of risk on a commercial product. But all of the Apples, NVIDIAs, they have specialized SRAMs, which are custom implementations of SRAM that are not the traditional 6T variant that we think of, be it for density, be it for retention. There are 7T, 8T variants that you can use. They're all looking at different memories, right? NVIDIA goes for HBM because it's a specialized DRAM that gives them performance. Apple has been looking at STT-MRAM, from what I know, which is another non-volatile memory with a different device function, but is also got basically identical benefits of what we were talking about. Yeah.
So if this heterogeneous memory technique gets brought to SoCs and microcontrollers more so in the future, you talked about the two coarse grain and fine grain power and energy optimization.
Yeah.
How would that reflect on the overall device power consumption? Let's say my controller uses 3.3 volts now. How would that reflect on the bigger scale? Or the Jetson uses, 12 watts or something like that?
Yeah. So I mean, you have to have at least an order of magnitude improvement to justify the cost of changing your design to a new memory technology. So my advisor at Stanford maybe gets some flack for it, but he always is pushing us to get 10x to 100x energy performance. Whatever the benefits we're targeting need to be that scale, and his motivations are correct. Every time I've had these interactions with industry, unless you show that level of benefit, think of all the engineering hours that have to go into making this transition. There's no way any company is going to justify that cost for 20%, because they can just improve their own design and get 10, 20% every year, year over year, right? Like every iPhone, the performance improvements are 20, 30, %. So in order to justify you know, a foundry developing a new process, a new full custom layout of a memory, a new circuit implementation for all of this power gating, performance optimizations, whatnot, plus then qualifying that to be commercially ready for, you know, hundreds of millions of devices to be sold. I mean, we're talking 100 to $500 million of investment. So you have to have really good performance benefits. So I think that's something that is important to think about, right? Like in academia and the research we do, we're trying to think about things that are 10 to 20 years in the future. 10 to 20 years in the future, that means we should see very large scale benefits, because otherwise, you know, next year in industry, they're probably going to get the same smaller scale benefit. And that's, I think, a really good example of, you know, you have to have kind of lofty goals and think of really cross-cutting innovations across the stack. That's how you're able to get those larger scale benefits.
Yeah, maybe a variation of Aidan's question is also that, you know, only a fraction of the total
Yes.
workload is on inference.
Yeah.
And then the other stuff is, you know, all the other interfacing with the physical world, other
Exactly, yeah.
general purpose computing.
Yeah. So has anyone heard of Amdahl's law? Yes. So can you explain, do you know what the like simple version is?
Yeah, essentially, if you have a speed up. If you have a quantifiable speed up in one area of your process, how does that reflect on the overall speed up of your system?
The simplest way is you're limited by the worst performing part of your system. So if we make our accelerator awesome in terms of performance and energy, the other stuff becomes the worst performing parts, and we're limited by their performance. So that's another way of stating that, which is, you know, you have to have these large performance improvements, because otherwise you're not really improving the overall system. If you're still, you know, if you do a 20% improvement of the worst X component, that's actually much better than a 10x improvement in the best component, if that best component is only 20% of your total system performance. So I highly suggest anybody, like Amdahl's law is a great way of, I wouldn't say doing your own homework and studies, but think about what's going to have the largest improvement on the worst parts. That's how you end up getting the best overall improvement.
Yeah, and in that case, the thing is the bottleneck keeps shifting, right?
Yeah.
So before the bottleneck was on hard drives, now the bottleneck is on inference. Now what Professor Radway is doing is he's shifting the bottleneck back out of inference back to the traditional function.
Yeah.
I'm wondering if like what timescale this is actually meaningful, or if you have an application where you need to be doing inference like very, very quickly.
Yes.
Like where does it actually come?
Yeah, so this is a good question. So I actually will talk about this in the next part about kind of compiler techniques, but you know, if you're thinking about doing something where you have these power gating events 10 to 100 times per layer or per model, then you need to be at least 1,000 times faster, right? Otherwise, it's a large portion of your time. So that is basically Amdahl's law as well. But if you go to say microsecond inference, then you need tens of nanosecond wake up and shutdown. That's actually very hard to achieve. But microsecond inference is also very, very hard to achieve, except for very tiny models. And in some of those situations, these bandwidth optimizations don't really matter as much anyway. So it's you know, I think this work is very much focused on taking, say, large scale models like LLMs and bringing them to the edge. For already highly tuned, optimized, you know, in sensor models, this may not be the right technique. Other techniques might be better. So it's understanding that as well, because of the overall, you know, what's your bottleneck? Okay, so I have about 15 minutes. Is that right?
Yeah.
Yeah. So I'm going to give a very high overview of the next part. There's a lot of slides, but I will skip a bunch of them. So I'm just going to jump right into this. So everybody knows who von Neumann was, right? Yes. Everybody knows the ENIAC that's sitting over in Moore. Okay. So if we think about what the ideal inference system is, we call it in my work, we call this a dream chip, right? It's something that's unachievable. That's like the best case that you dream of in your sleep. but you'd have some massive memory that could fit the entire workload. So n times m is the size of the workload, fit the entire workload on chip. You have compute, you have buffers to do the intermediate values, and that's it. And everything would be, very low energy because you're accessing all your weights at low energies instead of using off-chip memories. So von Neumann had the exact same dream in the 40s, figured it was unrealistic, and went to hierarchy in the memory systems. We face the exact same problems today as almost 100 years ago. The workloads have shifted, but we still need to think about how we can overcome those types of bottlenecks in building our systems. And I gave the example of like the RAM versus traditional memories, like 10x to 100x EDP benefits. This is the same for advanced node GPUs as well. If you look at HBM, it's like 65-ish picojoules per read, whereas the computation is 0.33 picojoules for an EBIT operation. So you're talking an order of 160x difference between accessing memory and doing your computation. So if you can read on-chip memory much lower energy than that 62.5 picojoules, you have major savings in your overall energy efficiency. Problem is that we can't actually build these dream chips. So there are companies that have tried to build wafer scale engines. This one company called Cerebras. It's a chip that's this big. It takes 30 kilowatts to power that chip. And it has a whole host of mechanical stability issues and whatnot. But even that wafer scale chip can only fit 16 gigabytes. I think their most recent one, they're going to scale it to 42. The largest language models are like hundreds of gigabytes, right? So even that massive chip is not a dream chip. So we have to look at how we think about multi-chiplet systems. And a lot of my work on multi-chiplet systems has basically been taking these ideas of very fine-grained power management and applying them not only on the chiplet, but inter-chiplet as well. And this changes how you would map and schedule your workload, because you care much more now about inter-chiplet network energy and the static power for that versus actually what's happening on the chiplet, because you've minimized the chiplet energy so much. So this is, again, the kind of bottleneck. What is the energy bottleneck? Instead of the idle power of your chiplets, it's how you think about your communication on your network.
You can just explain again.
Yeah. Yes, sorry. When I say chiplet, I just mean a chip, a custom IC. There is this technique called 2.5D integration, which is basically taking multiple of those dies and putting them in the same package on what's called an interposer. And the idea is that like today's GPUs, ideally we would want it to be larger than what's called the reticle limit, the max size that we can fabricate traditionally. So you need to separate that into smaller chiplets, smaller chips, and connect them very tightly to have the same performance or energy efficiency of that ideal larger chip. So if anybody's seen, has anybody seen the die photos of the B200s, NVIDIA's latest GPUs? It's actually two GPU die of their original die stitched right next to each other instead of one larger die. So those would be called chiplets. So this also applies a lot for edge systems now. We're starting to see chiplets in the edge as well because of cost reductions, right? So at the edge, you really care about making things affordable because it's mostly consumer electronics. Breaking up a large chip into smaller chiplets is a way to reduce overall fabrication cost. So I won't spend a ton of time on, let's see. I won't spend a ton of time on what we're doing, but the basic idea is that if we can take our system for a given machine learning model and optimize the performance on this idealized dream chip, that gives us the lower bound, the best possible performance we could achieve. That lets us actually do some clever solver optimization, some clever techniques on how we would think about optimizing, compiling a workload onto a multi-chiplet system. And those let us basically create a optimization loop where we can figure out what the ideal multi-chiplet system is that gets as close as possible to this dream chip for a given workload, given architecture, and then given memory size and die integration technique. And this ends up being something that's slightly more on the math side. So we look at mixed integer quadratic programming, which is a subset of constrained optimization techniques. What's the course in Nick Matney's course, right?
Yes.
Yeah, I don't know the number. Yeah. So I randomly took a optimization course in my PhD, and this ended up being a large part of my dissertation work. So take interesting courses like that might be slightly outside of your field. A lot of compiler techniques, VLSI, design, EDA tools, etc., used constrained optimization because you can have provable guarantees on the bounds that you're either an optimal solution or close to optimal. And so those are useful mathematical formulations and solving approaches. So basically, the takeaway from this should be, if we look at compiler optimization, it actually becomes somewhat of a complex math problem, even for something as simple as, say, how do I best take like a 7-layer neural network and assign it to a 3-chiplet system? If you want to prove that it's the best possible approach, you need something like this. Otherwise, you're evaluating, potentially millions of possible mappings and schedulings, and you can't reasonably do that in a reasonable amount of time. Some ideas is that we can use quick pump starting to basically jumpstart our optimization. So does everybody know what NP hard or NP complete workloads are, right? Like there's the idea of stuff that's solvable in polynomial time and then non-polynomial. Constrained optimization, non-convex optimization is NP hard. So we don't actually know how long it could take. But the key insight is that if we can solve that dream chip case, which is actually relatively straightforward to solve because it doesn't have a lot of the complexities, that gives us this lower bound. If we can use a heuristic to get a warm start solution that we prove is a valid solution that's very close to that lower bound, we can terminate basically instantly because we say, okay, we know that the bound is 5% or whatnot. If we actually let the solver try and solve everything exactly, it can take 10,000, 100,000 times as long. So using clever heuristics plus robust mathematical techniques let us look at some of these compilation problems in a different light and let us make meaningful optimizations. So that I will leave on that part of the work. But I think one thing that I'd like to point out is like this idea of scalability, right? We said our memory is scalable because it's dense and you can lithographically scale it. But the other way that you could potentially scale it is by having many layers of devices. So I'll talk on some of that at the end. If you can increase your capacity by increasing your devices per chip by doing 3D integration instead of 2D integration, that gives you an increase in your per chiplet capacity. If you can also think about improving your chiplet links or your chip-to-chip links to be more energy efficient and higher bandwidth, that gives you another scaling axis. And the idea is that somewhere in this cross product, if we can design a system that leverages both, that sidesteps these miniaturization and memory wall issues that we've had at the beginning of the class, right? Because even the RM system that I presented, it was one chip that was 12 megabytes. Well, how do you do a 24, 36, 200 megabyte model, right? You need something that either scales up the capacity or reduces the chiplet costs so that you can have the right size chiplet to solve your problem. So I think the takeaway there is that, when we think about multi-chiplet systems, it's a co-design problem. It's not only how do we design the individual chiplet itself, but how do we design our compilation approach to map, schedule, and utilize those different chiplets effectively. And this is becoming, I would say this is very, very common for edge learning systems. This is becoming much more common now because even for edge systems, we are running into cost and scalability issues. So the last part that I will talk briefly on is how do we actually do this on chiplet or on chip increase in memory? And the answer is that we have to look at new transistor and memory device integration techniques. So things that would happen in the sync center, right? New fabrication approaches in order to integrate more devices on chip. I won't go into the nitty-gritty of how it's actually done, but the basic idea is that let's say you can add, you start with your silicon CMOS layer. This is the cross section of a normal chip. Everything is usually connected with metal layers to the back end of the line. And then you have your front end, which is on the actual silicon wafer. If you can add RAM, that gets you nice benefits, right? We showed that if you can add this RAM process, there's all of these system level and chip level design benefits. What about adding additional transistors like carbon nanotube FETs or multiple layers? What if I do 2 layers of RAM and 2 layers of additional transistors? This actually has substantial performance benefits in addition to the density benefits. And the main reason is that effectively what you can do is that if you had your original design, or this is an example of a RAM array. So let's say you have your readout circuits, and then you have your actual storage bit cells. They take up some amount of area in that silicon in a traditional silicon approach. Using new devices, we can move that into those upper tiers, and we free up this front end space. So now we can design new circuits to use that space to give us performance improvements. We can increase our bandwidth. So this was actually demonstrated in hardware with collaborators at MIT and a foundry in the US. ISO footprint, ISO node, using the same memory technology, you can have 4x bandwidth increase. That's pretty substantial, right? That means you get basically a 4x speed up if you design your compute system correctly, in addition to the energy benefits that I talked about earlier. So this is a whole area of what I call future hardware systems, which is how do we look at integrating many chiplets via continuum of integration technologies, each with various device technologies in the back end of line, so that you can create what we call 3D mosaics or monolithic stacked and assembled ICs. And then this has a whole host of related problems. How do you design the accelerator? How do you design compilers? How do you utilize the correct memory technologies for each of these components and determine that design optimization? So I think there's very interesting set of research questions around that. So if anybody's interested in working in these areas, feel free to reach out. So yeah, that I think is the end of what I'll cover for today. But yeah, happy to take any questions.
Let's give let's take a couple of questions.
Yeah.
So my question was when you're building chip and scaling on the 3-dimensional space.
Yeah.
There's the problem of noise between different circuits become much more.
Yeah, so noise is okay. So we already deal with that pretty well in traditional 2D circuits because we have all those metal layers to begin with throughout signals. So we know how to handle coupling and other parasitic issues. The biggest problem is thermal. So if you have a GPU today, it's like 3,000 watts for the B200, I forget which, BG200 into the system. The GPU itself is close to 1,500 watts. So it's very hot. They get very hot. Now imagine if I tried to do that where I have 2 of those directly stacked on top, or 4, right? Now I have increased my power density by 2x or 4x. That can actually cause substantial issues, thermal mechanical issues. It can cause the devices to not perform correctly, whole host of things. So we actually need to think about, if we do this, we have to make things more energy efficient so our total power is better. But we also have to figure out how to get heat out of that stack more efficiently than we do with the 2D system today. So that's definitely the biggest challenge versus, say, signal integrity is the term for what you're talking about. Signal integrity, not as big of an issue relative to that challenge. Yeah.
One of the things that you were mentioning before about ASICs is that you need a demand that's high enough in order for it to pay off for the R&D costs of the ASIC.
Yeah.
So how well does this memory architecture lend itself to like general inference workloads so that the demand is high enough?
Yeah, so I think that's part of the reason I glossed over this of like we had multiple versions of these RM systems is that machine learning models were changing over time. So we wanted to build a new system that both addressed the newest models, but was also backward compatible. And this is a constant problem, right? Like every time the guys in this building upstairs will release some new latest and greatest ML model, it's not going to be optimal on the hardware that they have, right? And it's going to take 2 years from idea to actual hardware tape out, like fab out and being ready to use, to go from a new algorithm to a new hardware model. So each of those tape outs that I showed, it's like a 2-year process. So there's always this lag with custom hardware. There's a huge area of research on this around design enablement and automation and reuse. Those are areas that are quite important to making ASICs kind of scalable. And so we've seen a lot of improvements in the last couple of years on those efforts, but this is still an open kind of research question in general. Yeah.
Like away by like your training sequence to like the RM or
Yeah, so we did the compression ideas to be RM aware, and also the idea of using SRAM as a buffer for updates that are time delayed. So you would accumulate updates in your SRAM and then only infrequently write them back to the RM. So in that sense, it was RM aware. And we tuned the algorithm update frequency based off of the characteristics of the RM. But there are many other compression techniques. There are techniques using what are called hyper networks, where you basically are doing pointers for updates instead of actually writing the values. That could work. It's an open area in general of how to do training for specific memory technologies. So I think it's a good area to research, for sure.
Yeah, so this is great. So I think this is something that is why I invited Professor Radway here today, was to complement now, to show you what the journey ahead is after you've got a taste for building, that kind of applications we are doing in this class. So one thing you can see is that there is, you have to become like a platform architect. You can't just say, oh, I'm just only going to do CS and I'm just going to do that part, right? You can, but that'll, like your career lifetime of how much ahead you can see becomes much smaller then, right? Because as you can see, the models themselves are changing so much. So this cross-layer optimization is a one technique, right? But that requires you to really have, you can see his knowledge is all the way from designing, like the materials to the transistors, all the way up to the algorithms, right? There's optimization, there is architectures, so that's the second thing is a follow-up would be look into Professor Radway's course, and that's the
5760. No, yeah, 5760. The semiconductor devices and circuit design.
Yeah, and then that's a good way to understand that stuff. And then if you're interested in this, also think about doing research in this area.
Yeah.
And that's a great way to start, right? Always have the young professor will take you very far. Okay, that's and so the talk we will have now on Wednesday will complement this. That's from a startup company called MemoryX.
Oh,
that's
yeah.
a spin-off from University of Michigan. And I've actually worked with them during COVID. It was very exciting. And they actually are selling chips now with in-memory computation. And so they will talk about their whole pipeline. And that's also just like that, like the co-founder was a PhD student, worked with his advisor, and now I think they crossed over 65 million in funding. But it's not to boast about that, but it just means that they got funding 7 months ago for some 40+ million. That means they have internships. Okay, so I asked them to advertise that too. So study the stuff, build your fundamentals here, get the right internships, have a good future. And that also, since we're talking about chips, today we'll hand out our TinyML laptop stickers. They are not so tiny, but so let's give Professor Robert Radway a hand. Thank you so much. This was super insightful.
Yes,
I learned a lot.